This is Physics 2211 Lab 2, the motion of a falling object. The purpose of this lab is to demonstrate the effects of the force of drag on an object falling from rest and predict a terminal velocity. The model of predicted motion that accounts for both gravity and drag will be the most accurate in depicting the observed motion of the object. For the model, we are dropping a balled up piece of paper from rest and allowing it to fall to the ground. And although we often tend to ignore the effects of drag in an attempt to simplify calculations, the force of drag does have an overall effect on the net force, which in turn will affect the acceleration. The methods used are tracker, which was used to quantify the change in position of the object by determining the position frame by frame, glow script, which was used to computationally iterate in order to predict the motion of the system, both with and without the effects of drag, and Excel, which was used to graph both the quantities of the observed motion as well as the quantities of the predicted motion. As for the fundamental principles used, we use Newton's second law, the definition of gravitational force, which is mass times g, which is 9.8 meters per second squared, and the drag force, where b is the proportionality constant. More on Newton's second law is that it's the momentum principle, and the net force experienced by a system is equal to the system's change in momentum over the change in time. From this, we derive our position update formula, as well as our velocity update formula, which are both used within the glow script code. As for our observed model, we used a tracker. The system is the ball of paper, the surroundings are everything else. The initial position we established as the origin. The initial velocity is 0 since it's dropped from rest. The time interval is from 0 to 0.3 seconds. The net force is the force of gravity plus the force of drag. And since we have a non-constant velocity, there is an acceleration. For our first predicted model, we ignore the effects of drag. So when we set our initial conditions, we set the mass of the ball as 0.005 kilograms, the position as the origin, and the initial velocity as 0 since it's dropped from rest, and we establish a direction with a unit vector. We edit our delta t. Our F net is going to be equal to just the force of gravity in the negative y direction, so we get negative g times the mass of the ball. The ball position will change according to the position update formula, and then we advance the clock by taking another incremental time step of delta t. For our second predicted model, we account for drag. So we set our initial conditions to be the same as the previous, except this time we will have b, which is the proportionality constant. We find this value through guess and check. We alter this value and run the code until the final position matches the final position of the observed model. Again, we edit our delta t. This time our F net is going to be slightly different because we're accounting for both gravity and drag. So we are adding those two values together. The ball position will change according to the position update formula, and again, we advance the clock by taking another incremental time step of delta t. Here are the results of the experiment. As you can see, the darkest blue is our observed model, which is tracker. The gray is the predicted model that accounts for both drag and gravity, which we can see most accurately aligns with the observed model. And then the lightest blue is just the predicted model that only accounts for gravity. So what exactly does all this mean? Well, a terminal velocity on a velocity versus time graph would be shown as a slope of 0 since it is no longer changing. Neither model truly predicts a terminal velocity as shown in the figures, but the model taking drag into account can be seen flattening out, and if the object was dropped from higher up, which would then allow it more time for it to hit the ground, a terminal velocity likely would have been hit. Since terminal velocity happens when the force of drag up equals the force of gravity down, this means that the net force would be 0, which in turn means that the acceleration is 0, which makes sense because a terminal velocity means the velocity is no longer changing. So what if we actually threw the object downward initially, and how would that affect the terminal velocity? If the object were initially thrown downward, it would reach its terminal velocity faster, seen in the steeper slope of the first figure, but the terminal velocity value itself would not be any different because it is still just a balance of the forces.